the present lecture, we will introduce Hofmann exhaustive methylation and elimination reaction. After that, we will discuss Hofmann versus Zaitsev elimination. Then we will discuss Hofmann-Martius reaction and Hofmann mustard oil reaction. We will then discuss oxidation of amines. We will discuss cope rearrangement, conversion of amines into sulfonamides and Hinsberg test. In the present lecture, we will also discuss phase transfer catalysts. Under this category, we will introduce them and give some examples of phase transfer catalyst. We will give a few reactions where these phase transfer catalysts are utilized, and the mechanism of those reactions will also be incorporated in this lecture. Now, we will start with the Hofmann exhaustive methylation and elimination reactions. Amines are methylated till quaternary ammonium salt is formed. This step is called exhaustive methylation. Quaternary ammonium salts react with silver hydroxide and form quaternary ammonium hydroxide in the second step. And in the last step, quaternary ammonium hydroxide undergo elimination upon heating and form a less substituted alkene as a major product, and all the three steps of exhaustive methylation and elimination have been depicted here. In step 1, methylation takes place up to quaternary ammonium salt stage. In step 2, the quaternary ammonium iodide or ammonium salt is treated upon with moist silver oxide, and there is formation of quaternary ammonium hydroxide, and in the final step elimination takes place to generate alkene along with a tertiary amine and water. Butanamine, a primary amine, utilizes 3 molecules of methyl iodide. You can see here that we have written here excess of methyl iodide. When normal butyl amine, a primary amine treated with methyl iodide, it utilizes 3 methyl iodide group and forms a quaternary ammonium iodide. This quaternary ammonium iodide reacts with silver oxide and forms quaternary ammonium hydroxide, which then upon heating produces 1-butene as the major product along with trimethylamine and water. If we start with an amine where 2 possible alkenes can be formed upon elimination, we find that the alkene which is less substituted is the major product. Like in this case, you can see this is 2-butanamine. This undergoes exhaustive methylation followed by treatment with silver oxide, and then upon heating undergoes elimination. There are 2 possibilities: formation of 1-butene and formation of 2-butene. 2-butene is a more substituted alkene, and it has been found that the major product here is 1-butene, which is a less substituted product. Now, the question arises that why is it that there is formation of a less substituted alkene, whereas in the earlier lectures you may recall that in case of Zaitsev elimination of alkyl halide, a more substituted alkene is the major product. As you can see in this particular case, this is 2-bromobutane. When it is treated upon with sodium ethoxide, it produces 2-butene as the major product, that is about 75% of the product is 2-butene and only 25% is 1-butene. Whereas, when the same kind of elimination takes place where the leaving group is a trimethylamino group, then the more substituted alkene is not the major product, but it is formed in a very small amount. Now, the question arises that why the Zaitsev elimination is opposite of Hofmann elimination. You can see here that this butanamine upon exhaustive methylation has formed trimethyl. This is not butanamine, this is 2-pentanamine which is undergoing this elimination reaction. Now, when this trimethyl, in this particular reaction, 2 products are possible. One is 2-pentene and the other is 1-pentene. 2-pentene is a more substituted alkene, whereas 1-pentene is a less substituted one, and it has been found that a less substituted alkene according to Hofmann elimination is the major product. In bimolecular elimination reactions, in the presence of either a bulky leaving group or a bulky base, hydrogen that is lost will come from the least branched beta carbon, as you can see here in this case. This is an alkyl halide and this is also a beta carbon and this is also a beta carbon. So, less branched alkene will be formed when this beta hydrogen is replaced and more branched alkene will be formed when this beta hydrogen is replaced. Now, the uses of Hofmann elimination. The reaction, this Hofmann elimination is used for the structure elucidation of natural products where nitrogen is present as a linear or cyclic nitrogen base. The nitrogen containing compound, the natural product, is first methylated and converted to corresponding quaternary ammonium iodide by exhaustive methylation and then it is subjected to elimination. For example, N-methylpiperidine after following above sequence of reaction forms 1,4-pentadiene which isomerizes to 1,3-pentadiene under reaction conditions. See what happens here is this is N-methylpiperidine undergoes exhaustive methylation and forms a quaternary ammonium iodide which upon treatment with silver hydroxide forms quaternary ammonium hydroxide and then undergoes elimination reaction. But since this is a cyclic amine, the bond breaks along this carbon and nitrogen and there is formation of a tertiary amine only. This tertiary amine again undergoes methylation and since it is a tertiary amine, it utilizes only one methyl iodide group. There is formation of quaternary ammonium iodide followed by formation of quaternary ammonium hydroxide and then elimination produces 1,4-pentadiene as the product. So, if a natural product has this kind of nitrogen function like in case of piperidine, then we know that by two set of exhaustive methylation and elimination reaction, we can separate the nitrogen function that is trimethylamine from the natural product and that is how we elucidate the structure of natural product. Now, Hofmann-Martius rearrangement. An alkylated aniline hydrochloride or hydrobromide rearranges to 4-alkyl aniline when heated to 200 to 300 degrees centigrade. This is N-alkyl ammonium chloride. The alkyl group from this nitrogen migrates to the ring at para position. But if para position of the ring starting compound is occupied by another substituent, then the alkyl group may proceed or may go to the ortho position also. In Hofmann mustard oil reaction, primary amines react with carbon disulfide to form a dithiocarbamic acid which forms alkyl isothiocyanates with when heated with mercury chloride. Alkyl isothiocyanates smell like mustard oil and that is why this reaction is called Hofmann mustard oil reaction. Here you can see this is a primary amine, it reacts with carbon disulfide and by following this sequence of reaction finally produces isothiocyanates. We will now discuss oxidation of amines. Primary and secondary amines undergo an oxidation, but useful products are not obtained because of side reaction. The oxidation of amine is done with hydrogen peroxide or with peracid. Tertiary amines undergo an oxidation. This is a tertiary amine. This reacts either with hydrogen peroxide or with peracid and forms N-oxide, a tertiary amine oxide. We will now discuss scope elimination, in which a tertiary amine oxide undergoes elimination to form an alkene and N-dimethyl hydroxylamine upon heating. Tertiary amine oxide can be prepared from tertiary amine by the reaction of amine with hydrogen peroxide or peracid. Amine oxide elimination is a syn elimination and proceeds via a cyclic transition state. You can see here this is a tertiary amine oxide. This upon heating forms an alkene and it is N-dimethyl hydroxylamine. As has been discussed, this elimination reaction and formation of alkene is a syn elimination, that is the removal of this dimethyl hydroxyl amino group and the hydrogen from the next carbon. Both of them are replaced from the same side of the molecule, and that is why this elimination is called syn elimination. We will now discuss the conversion of amines into sulfonamides. Primary amines react with aryl sulfonyl chloride and form N-substituted sulfonamide, whereas secondary amines react under similar conditions to form N di-substituted sulfonamides. Tertiary amines do not react with aryl sulfonyl chloride. The reason is very clear, that they do not contain any hydrogen attached to nitrogen. You can see here there is no hydrogen, that is why no reaction takes place between tertiary amine and aryl sulfonyl chloride. This reaction of amine with aryl sulfonyl chloride is used for the separation of three classes of amines. Here this is amine, the lone pair of electron of which attacks the sulfur of aryl sulfonyl chloride, followed by a series of reaction to generate this N-alkyl sulfonamide. Sulfa drugs are sulfonamides and they are antibacterial agents. They are used, actually this reaction is a useful reaction for the synthesis of sulfa drugs. We will now discuss the Hinsberg test, which is used to distinguish between primary, secondary and tertiary amines, and this is based upon sulfonamide formation. In the Hinsberg test, an amine is reacted upon with benzene sulfonyl chloride. If a product formed, if the product is formed, the amine can either be a primary amine or a secondary amine, because tertiary amine do not form stable sulfonamides. We have already discussed primary and secondary amines will form product because they have hydrogen attached to nitrogen. If sulfonamide that forms dissolves in aqueous sodium hydroxide solution, it is a primary amine, and if the sulfonamide formed is insoluble in aqueous sodium hydroxide, it is a secondary amine. The sulfonamide of a primary amine is soluble in aqueous base because it still possesses an acidic hydrogen on the nitrogen, which can be lost to form a sodium salt. You can see here that this is a primary amine reacting upon with benzene sulfonyl chloride forming sulfonamide. When reacted with sodium hydroxide, there is still one hydrogen left which forms a salt by replacement, and that is why this sulfonamide of primary amine is soluble in water. Whereas, if it is a secondary amine, then it forms sulfonamide, but this is not soluble in water because there is no hydrogen on nitrogen which can form salt. Tertiary amine, you already know that they do not react with benzene sulfonyl chloride at all. So, by this method we can separate or we can identify whether the amine is a primary amine or a secondary amine or a tertiary amine. We will now discuss a new topic of phase transfer catalyst. The phase transfer catalyst in chemistry is a catalyst that facilitates the migration of a reactant from one phase to another phase where the reaction occurs. Phase transfer catalyst is a special form of heterogeneous catalysis. These catalysts are the catalyst used in those organic reactions which involve inorganic reactants. They become essential because organic reactants stay largely in the organic layer, while the inorganic reactants stay mostly in the inorganic or aqueous layer. Hence, the yield of such reactions remain very low in the absence of phase transfer catalyst. These phase transfer catalysts are usually alkylated ammonium compounds with a few long alkyl chain. These compounds are soluble in both organic phase and in inorganic phase and can freely move from one phase to another. They also have a property of being able to exchange ions with the inorganic reactants. Hence, they are able to transfer the ion needed for the reaction to the organic phase where they may react with the organic reactants. Hence, they bring about a great increase in the yield of reactions of organic reactants with inorganic ones. An example of phase transfer catalyst is this example. where you can see that this is a tetra alkyl ammonium chloride. These three groups are the ethyl group, alkyl carbon chain is there with 16 carbons. You can see the atomic model of this ball and stick model of this phase transfer catalyst. Another example of phase transfer catalyst is triethyl benzyl ammonium chloride, also called TEBA. Here you can see the one group is benzyl group and three other alkyl groups are ethyl groups, and this TEBA has 13 carbon atoms in the molecule. As a result, it is highly lipophilic in nature. The catalyst may be synthesized from N diethyl benzyl amine upon treatment with ethyl chloride. We will now discuss the mechanism of action of phase transfer catalysis. For that, you can see here we have taken two solutions. One is the organic layer and the other is inorganic layer or aqueous phase. Now, the organic molecules will dissolve only or will remain in organic layer, and inorganic molecule will remain in the aqueous layer. They will not pass on to another phase, or we can say only a small percentage of molecule will cross the boundary line and will undergo reaction. So, hardly any reaction takes place. But what happens when we add a phase transfer catalyst into these two phases? This is the organic phase and this is inorganic phase. If we add phase transfer catalyst into this solution, then the red dot actually depicts PTC, and you will see that slowly these red dots will intermingle between both the phases, that is in the organic layer as well as in the inorganic layer, and while travelling from inorganic layer to organic layer, they will pass on the reactants also, and that is why the reaction takes place in good amount and we get a good yield of the product. We will discuss the same mechanism of action with the help of an appropriate example. Here you can see that 1,3-propane diol reacts with sodium sulphide to form thiocyclobutane. The organic compound remains in organic phase. Here you can see that this is 1,3-propane diol and this dissolves only in dichloromethane, that is the organic layer. We are using sodium sulphide which dissolves only in water. So, in a solution we have two phases, one is the dichloromethane phase and the other one is water or aqueous phase. In dichloromethane we have this propane diol and in aqueous phase we have sodium sulphide, and that is why there is no reaction possible between these two reactants unless we add some PTC or phase transfer catalyst. Now, see what happens when we add the phase transfer catalyst into this solution. The phase transfer catalyst exchanges its chloride ion for the sulphide ion, which are transported from inorganic phase to the organic phase where they are needed for the reaction. The sulphide ions transported to the organic layer by phase transfer catalyst and are now able to react with organic reactant and give the product, that is thiocyclobutane. The catalyst is also able to transport out the hydroxyl ion formed into the aqueous layer, so that the reaction keeps on going in forward direction. Thus, we see that phase transfer catalyst is able to carry the sulphide ion into organic phase to a great extent, which otherwise in its absence was not possible. These sulphide ions are able to take part in the reaction. Thus, addition of phase transfer catalyst increase the yield of reaction greatly. We will now discuss another example where nucleophilic substitution reaction of normal octyl chloride with sodium cyanide is taking place. See, normal octyl chloride is not soluble in aqueous phase, whereas sodium cyanide remain in the aqueous phase. So, if we treat the two reactant together, no reaction takes place. But if we add a phase transfer catalyst like tetra normal butyl phosphonium bromide into the reaction mixture, then the product is formed. The reason here again is that the bromide minus ions of this PTC or phase transfer catalyst are exchanged with that of cyanide ions, and then this phase transfer catalyst will carry cyanide ions to the organic phase, and then the reaction will take place. Here you can see this is sodium cyanide and this is tetrabutyl phosphonium chloride, the phase transfer catalyst. This phase transfer catalyst in aqueous phase reacts with sodium cyanide and produces tetrabutyl phosphonium cyanide, which enters the organic phase or organic layer and then reacts with alkyl halide to form alkyl cyanide. In the process, tetrabutyl phosphonium chloride is formed, which is again transported to the aqueous phase, and in this way the reaction keeps on taking place. The catalyst tetrabutyl phosphonium chloride contains highly lipophilic butyl group, which makes the compound soluble in organic solvent. It also has a polar phosphonium salt, which makes the compound soluble in water as well. Here is another example in which cyclohexene reacts with the chloroform and NaOH and forms this product in presence of a phase transfer catalyst. Well, in this particular reaction of the synthesis of 7,7-dichloronorcarnane under PTC conditions, the reaction between sodium hydroxide and trihaloalkane takes place first, and there is formation of sodium salt of this trihaloalkane, which upon treatment with this phase transfer catalyst forms a dihalocarbene. This dihalocarbene reacts with this cyclohexene and produces 7,7-dichloronorcarnane in good yield. So, with this we can say that phase transfer catalysts are very useful in the preparation of a number of products where the two reactants are not soluble in one phase. One of the reactant is soluble in organic phase, whereas the other is soluble in inorganic or aqueous phase. So, with the help of this phase transfer catalyst, this kind of tedious reaction can also occur. Now, to summarize, in the present lecture, we have discussed Hofmann exhaustive methylation and elimination reaction. We have discussed the product formed in Hofmann elimination versus Specefgoc elimination. That is, in Hofmann elimination the product is a less substituted alkene, whereas in Specefgoc elimination the product is a more substituted alkene. We have also discussed Hofmann-Martius rearrangement and Hofmann mustard oil reaction in this lecture, and then we have discussed oxidation of amines, and under this category we have also discussed Cope rearrangement. Then conversion of amines to sulfonamides, which are very good antibacterial agents and are used as sulfa drugs, and then the Hinsberg test, which is used to identify whether the amine is a primary amine or a secondary amine or a tertiary amine. And then we have discussed phase transfer catalyst. Under this category we have introduced them, given some examples of phase transfer catalyst, some reactions which involve phase transfer catalyst and mechanism of their action has also been introduced here in this lecture.